So for these next 3 lectures, we're going to be talking about the heat. And the way these are going to work, it's going to be the same for cold and it's going to be the same for altitude, is that it's going to be 3 mini lectures for each part. So we'll have 3 on heat, 3 on cold, 3 on altitude. And so when it comes to each of these, we're going to have acute responses, we're going to have chronic responses, and then we're going to talk a little bit about illnesses. Now, I will let you know that a lot of the slides that I use for this lecture are taken straight from what I use in 480. However, we go into more detail if you take 480 or 580, the environmental exercise physiology class. So here are the 3 outcomes for this lesson. And so we want to start off with heat and the cardiovascular system. And really, that's where the demand comes from, or the stress. It's put under the cardiovascular system. And so there's 2 demands that the cardiovascular system faces. One, as always, when you're exercising, the cardiovascular system needs to provide oxygen to the working muscle. However, the second demand is that there's an increase in skin blood flow, and this happens so that we can dissipate heat. Okay, it's all right if we increase our core temperature up to a point, but if we get too hot, then those high temperatures can cause some serious problems, breaking down proteins, causing nervous systems to not work right, that sort of thing, which is just bad news. So, what are the issues with those 2 demands? Because if you think about it, they're opposite. They're competing against each other. And what I mean by that is if I'm sending blood to the skin, I'm not sending it to the muscles. If I'm sending blood to the muscles, I'm not sending it to the skin. And so we've got to balance those out. And so if we decrease blood flow to the active muscle, what's going to happen is we're not going to be able to exercise as long, as hard, as high of an intensity. And so this might be caused by stroke volume decreasing, which leads to an increase in heart rate, right? So we can counteract a low stroke volume by increasing heart rate. The problem is that we hit max heart rate at a lower intensity. Then the other question, and one that still hasn't been completely figured out when it comes to heat, and we'll talk about this in a couple minutes, is it the decreased stroke volume causing the increased heart rate, or is it the increased heart rate causing the decreased stroke volume? And the research is mixed on that, okay? And so one of the things that ends up happening is that cardiac output ends up being higher in the heat at a given workload. And this is because we're sending more blood to the skin than we would otherwise. Consequently, we have a lower VO2 max. We hit it at a lower intensity as well. So we tap out our heart rate. We hit our max heart rate at a lower intensity. Therefore, we're using less oxygen. Therefore, VO2 max is lower and occurs at a lower intensity. So let's go back to steady state. Whoops, I skipped a slide. Remember, for steady state, that means we've just got a constant oxygen requirement. And if we're using the metabolic cart, we can see this because VO2 will be constant and or heart rate will be a constant. However, heat affects this, and I want you to look at this figure here. So on this figure, and this is right out of your textbook, we've got time on the x-axis and we've got percentage of 10-minute values on the y-axis. And so what they've done in this study is they've had subjects exercise at a constant intensity for 50 minutes. Okay, at 10 minutes in, they've assumed that they've reached steady state, and so they set that as their baseline. And they've got 5 different variables on this figure: heart rate, cardiac output, blood volume, mean arterial pressure, and stroke volume. Now I want you to take a minute, and what do you see is going on in this figure? Okay, so there's a few things that stand out. One, cardiac output remains relatively constant. Okay, blood volume decreases a little bit. That shouldn't be surprising because they're exercising in the heat. Okay, pressure drops a little bit, and we can get into why that happens later. Basically, you're having dilation to help get blood to the skin, to minimize the work of the heart, that sort of thing. But with cardiovascular drift, notice that heart rate increases, and then over the course of about 50 minutes, or actually 40 minutes from our baseline values, heart rates increase by about 15%. Not surprisingly, since we have constant cardiac output, stroke volume has decreased by about 15%. So the question is, what's causing this? So as we said, during prolonged steady state exercise in the heat, we have an increase in heart rate and we have a decrease in stroke volume. This is referred to as cardiovascular drift, or CV drift. So the million-dollar question is, well, why does this happen? And the answer is, we're not completely sure. There's really two theories behind this. One is that because we have increased skin blood flow, that's going to decrease venous return. And if we have a low venous return, that means less blood is returning to the heart, which means there's less stroke volume. So that's one. The second one is that increased temperature speeds up metabolic activity anyway. And so that's going to cause your heart rate just to increase. So high temperature, increased heart rate. We talked a little bit about this with EPOC, about how your heart rate and breathing are elevated in part due to the high temperature, the high core temperature. This might also be occurring with cardiovascular drift. And so because you have high or an increased heart rate, there's less filling time. And if there's less filling time, that means stroke volume is going to decrease. Now, as nice as it would be to say it's one or two, I think it's primarily one, but two definitely plays a role. I don't think it's just one of them by themselves. And so this is something else that we'll see or experience, or a person will experience as they exercise in the heat. The effect or the magnitude of cardiovascular drift is increased by the magnitude of the ambient temperature. So you might see this a little bit in slightly warm temperatures, but if you're exercising like in 40 degrees Celsius, 105 degrees, you're more likely to see the cardiovascular drift, or it's going to be more pronounced.